Please go ahead and introduce yourself.
Hi, my name is Andrew Huang. I'm Hao Young Yu.
I'm Albert Tao.
I'm Joshua Yu.
I'm Deepak Party.
And you are from?
Adlai Stevenson High School from Illinois.
Thank you. Over here on the judging side, I'm Karen Bliss. I'm an assistant professor at Virginia Military Institute.
I'm Dan Connors. I'm a research staff member at IBM Research.
I'm Kelly Black. I'm in the math department at the University of Georgia.
Amanda Babson. I'm the Coastal Climate Adaptation Coordinator with the National Park Service.
Chris Bergman. I'm an associate analyst with the Liquids Industry Service.
So you'll have 15 minutes for your presentation. I will signal you when you've got 2 minutes remaining. After that, we'll have some questions from the judges, and then you'll be done. So please begin.
Thank you very much. All right, so our presentation is called Raining Down on Rising Sea Levels. So we go forth. So since their inception in 1916, national parks have become a symbol of America, inspiring generations of Americans through their natural beauty. And for the past 100 years, we see that the National Park Service work to maintain our national parks and educate Americans of their history. Today, however, national parks face an impending problem, the threat of climate change. In this problem, we were tasked to model the impact of climate change on these 5 national parks listed above. Over the course of our presentation, we will discuss modeling sea level change and its ramifications, discuss the vulnerability of each park to other climate-related phenomena, and forecast the number of future visitors, while also discussing ways to appropriate limited funding to all the parks to combat the aforementioned problems. For part 1, we were tasked to model to predict the sea level change for each of the 5 national parks listed above in the upcoming 10, 20, 50, and 100 years. Furthermore, for each of the national parks, we assigned each park a high, medium, or low risk rating for each year based on the threat of sea level change to each of the park. So there were 2 main assumptions that we worked under. The first being that we can discount temperature in any sea level change model because of the short duration that our model runs under. When we actually plot yearly temperature for the past couple of decades, we find that less than a 0.1% variation can be attributed to any standard run of best fit. And being as such, because our model operates under the short term, short run, we can discount it and instead base our model off on a set of collection of the data from the National Oceanic and Atmospheric Administration. Data shows that over the course of 100 years, the mean sea level change per year falls within overlapping 95% confidence intervals, and being as such, we can extrapolate a similar pattern and similar trend for shorter models under a few centuries. So, being as such, we can actually find the standard deviation and the mean sea level increase per year and create a normal model for the spread of possible sea level increases T years from now, as shown above. And furthermore, we set benchmarks for a sea level increase that suffices a high risk and medium risk. The high risk benchmark that we set is a 300.8 millimeter increase and 91 millimeter increase for a medium risk. These benchmarks that we set up were as followed because a 300.8 millimeter increase was associated with a high risk for humans. It's approximately a 1 foot increase, which is dangerous to humans, and a 91.44 millimeter increase was dangerous to the ecosystem present at each of the national parks. And so to show an example of how we applied our model, we can look to Acadia National Park. Now, Acadia National Park has a mean sea level increase of 2.178 millimeters per year, or mu, and a standard deviation, or sigma, of 0.111 millimeters per year. And when we substitute in these values, we see that in 10, 20, 50, and 100 years from now, we can see the probabilities of seeing the following high, medium, or low risks. And so, in general, we see that for Acadia National Park, for example, in the 10 to 20 years from now, we see that it's at a low risk, but towards 50 and 100 years, that's when it starts tending towards a medium risk situation. So these normal models were situated as such. It's the summation of T distinct normal models to account for across all T years. And if we assess the validity of our model as a whole, we should note that our model only takes meaning from short time periods, which mean from a couple of decades to a couple of centuries. For extremely small time periods, we should note that our model shows an equal probability of each of the risks being likely, so it needs to be sufficiently large, which means at least a couple of decades, one sufficing as such. But correctly, for large periods of time, our model accurately predicts that all parks will tend towards a high risk of danger. But holistically though, when we speak of our model, it maintains a strong level of accuracy for the time period we're interested, 10 to 100 years. If we look to the 68, 95, 99.7 rule, and we have a simple t-test, we know that 99.7 of all possible cumulative sea level increases should be no more than 3 times of each site's standard deviation. So when we take the greatest standard deviation across all sites, which happens to be 0.628, then we know that it will be only off by a factor of 18.844 millimeters. So, and then in 100 years too. So as such, we can apply our model to all the locations to arrive at the following general assessments of all 5 parks listed above and hold them to a high level of accountability. Up next, discussing part 2 will be Hao Yan Yu.
Thank you, Andy. For part 2, we were asked to develop a mathematical model that assigns a vulnerability score to any coastal national park and takes into account the likelihood and severity of different climate-related events. And furthermore, we were asked to assign a vulnerability score using our model to the 5 national parks in part 1. When developing our model, we considered 3 factors: heat index, hurricanes, and air quality index, because these were deemed the most significant. We developed a severity index for each of these factors from a scale of 0 to 100, and then performed a weighted average for each of these indices to come up with our final vulnerability score. We also assumed that the number and severity of hurricanes would remain constant for the next 50 years, because in the past century, there has been no statistically significant trend in the number or the severity of hurricanes. For the severity index of the heat index, denoted SI sub HI, we used a 4-parameter logistic regression. Based off of the heat index chart, we established references of 80 degrees, 90 degrees, 103 degrees, and 124 degrees as levels of caution. We then assigned each of these references a value of 25, 55, 86, and 98 on our severity index, thus giving us the equation shown on the left. For the severity index for hurricanes, denoted SI sub H, we consider 2 major factors: the intensity of the hurricanes, H, and the return period of the hurricane, tau. As the intensity increases, the threat of the hurricane also increases. However, as the return period increases, the threat of the hurricane decreases. So SI sub H is directly proportional to H and inversely proportional to tau. In order to make this fit our desired range, we set the constant K a value of 100. For the severity index for air quality index, denoted SI sub AQI, we used a linear combination of 3 variables. The first being the average AQI value, mu, the average maximum AQI value, big M bar, and the average minimum AQI value, little m bar. In order to take the average of these, we gave them weights of 2 to 1 to 1. And in order to make it fit our desired range, we scaled it down by a factor of 2.7, giving us the equation on the very right. We noticed that these severity indices tended to vary based on its location within the nation. For example, the effect of hurricanes is much less in the West Coast than in the East Coast, which is reflected in the weights that we gave to it. We also saw that the effect of heat index is relatively constant throughout the nation. Thus, we gave both of these a value of 0.5 in the weights, and the other weights followed accordingly. Now, Albert Cal will present the rest of part 2.
Thank you, Hao. So, in order to validate our model, we compared the quantitative vulnerability scores with the qualitative aspects of each park that suggested risk. In the table above, you can see the severity indices for each of the factors, and finally the vulnerability score for each of the national parks. However, as Hao mentioned before, there is a significant difference, geographical difference between the East Coast and the West Coast, mainly that the West Coast has a lack of hurricanes, which lowered the vulnerability score of the West Coast national parks greatly. In order to adjust for this, we set a lower bound for the West Coast than the East Coast, and divided by this bound to find the adjusted vulnerability score for each national park. The adjusted vulnerability score for each national park is shown in the table there as well. In order to assign meaning to this adjusted vulnerability score, we set an adjusted vulnerability benchmark score of 1, which would prove useful in part 3. We reached this number through the examination of risk of each of the national parks. Padre Island experienced dangerous widespread flooding in both 2014 and 2015, while Acadia National Park is a Class 1 area under the Clean Air Act, which means it is in a critical state with regards to air pollution. These 2 parks are the ones with vulnerability scores that are greater than 1, which makes sense given the conditions. Cape Hatteras and Olympic National Park are also close to having an adjusted vulnerability score of 1, but Kenai Fjords is not close to an adjusted vulnerability score of 1 at all, so it is not at risk. The final section of part 2 was future projections of vulnerability. To do this, we projected changes in each of the separate indices that determine vulnerability. One of our assumptions before was that hurricanes would not change in change significantly in severity or frequency over time. So we assume that hurricane severity index would stay constant. For heat index, we used a linear model to model the heat index over time for each of the national parks because a linear model fit the data best. Once we had the linear models for each of the national parks, we averaged them to create the final heat index equation and plug that into our formula for severity index of heat index. For air quality index, we used a logarithmic model because that was the model that fit the data best. We used a logarithmic equation for each of the national parks' min, max, and average air quality index, and averaged them together to find the average logarithmic equations. And once again, using the equation that Hao Yang mentioned for severity index, plug those in and calculate severity index for air quality index. Using those three future projections of indices, we can find the vulnerability score in the future. Now, Joshua Yoon will introduce part 3.
Thank you, Albert. In part 3, we were given 2 main tests. First, we were asked to model the number of visitors in each park as a function of time, considering the results from our previous results, because each national park has risks of dangerous climate-related events that may impact the visitors that wish to visit the park. Also, we were then asked to use the results of our model to advise the National Park Service on how they should distribute limited funding between the 5 parks. In order to model the number of visitors each park would have in the future, we decided to use a linear regression as it best fit the current data trend. We also considered the adjusted vulnerability scores mentioned by Albert in part 2 because we decided that if an adjusted vulnerability score was above the benchmark of 1, it would discourage visitors from attending the park because the risk of climate-related events were higher than most parks. Now, we also determined that if the adjusted vulnerability score was below the benchmark of 1, then it would not play into consideration for potential visitors. So here we have our linear regression for Kenai Fjords National Park. And also in the chart, we have the values of each of the variables, coefficients in the linear regression for each of the 5 sites, as well as their respective vulnerability scores. As we can see, in Acadia and Padre Island, we have adjusted vulnerability scores that are greater than 1. So these were taken into consideration on whether visitors would decide to attend this park or not. To present how we use this information to advise the National Park Service on how they should distribute their limited funding, we have Deepak Mukherjee.
Thank you, Joshua. Once we calculated the projected number of visitors for each site after 20 years, we generated a visitor index for each site as well, which is derived by dividing that site's projected number of visitors by the greatest projected number of visitors among the 5 sites. After doing so, we assigned vulnerability indices for each site by dividing its adjusted vulnerability score by the highest vulnerability score of all sites. Using these 2 indices, we calculated a financial utility index. We calculated a financial utility index, which is the sum of the visitor index times 0.75 and the vulnerability index multiplied by 0.25, a 3-to-1 weight. Once we calculated the financial utility index to determine what percentage of funds should be allocated to each site, we divided that site's financial utility index by the sum of the financial utility indices for all 5 sites. To heuristically test the validity of our model, we compared the vulnerability scores and projected number of visitors for the site with most funds allocated and least funds. Our model suggested that Acadia received the most funding, approximately 30%, while Kenai Fjords was allotted the least, 8.82%. Acadia has the highest adjusted vulnerability score and one of the highest projected growth in number of visitors, while Kenai Fjords has the lowest adjusted vulnerability score and one of the smaller growths in projected number of visitors. So it stands to reason that Acadia should receive much more funding than Kenai Fjords. In summary, in each of our parts, we were tasked with analyzing real-world data and their pertinence to a global problem facing all of us, rising sea levels and climate change. In part 1, in assigning levels of risk to each of the 5 national sites, we found Padre Island and Cape Hatteras to be in most risk, while Olympic and Kenai Fjords are in low risk. In part 2, taking heat index, hurricanes, and air quality index into account, we deemed Acadia and Padre Island to be in critical condition, as seen by their high adjusted vulnerability scores, while Olympic and Cape Hatteras seemed to be approaching critical condition. Meanwhile, Kenai Fjords was in a safe, steady condition for the future. We modeled the projected number of visitors over time in Part 3 and utilized that projected number with vulnerability scores to allocate funds optimally to each site. The model allocated Acadia and Olympic the most funds, followed by Cape Hatteras, and while Padre Island and Kenai Fjords received substantially less funding than the first three. Now we'd like to take a moment to thank the Moody's Foundation for providing us with such a wonderful opportunity, along with Coach Kim and Stevenson for giving us the opportunity, support and encouragement to get this far. Thank you.
I have a question about, in the paper, it's on page 6, but on your risk assignment model, for question 1. I'm not sure I fully understand how you made this determination of low, medium, high. So can you walk through like exactly how those determinations were made?
Well, a 300.8 millimeter increase is the same thing as a 1 foot increase, and a 91.44 millimeter increase is the same thing as a 0.3 millimeter increase. And we collected data from the National Geographic, which found that a 1 foot increase per century would be associated with a high threat towards human life, while a 0.3 increase, well, 0.3 feet increase would be dangerous to the park's operations and towards the ecosystem and biodiversity of each park. So
those were the cutoffs.
Yes.
And then how did you decide? So I heard you saying something about you took the mean sea level and the standard deviation, and then you computed what? How did you determine then? Yeah.
Well, we have a 95% confidence interval, so from that we can find the mean sea level increase for every year and the standard deviation approximately also. And when you combine those two, we can put a normal model which shows the average distribution, we can say, of the mean sea level increase T years from now with like how far off that estimate would be. So that's the actual normal model we assign. And the reverse model, when we substitute the numbers of mu, the mean sea level increase, and sigma, that shows our bounds of where that mean sea level increase would be in year T, and then depending on where that is in the distribution of what possible values could also see within that year, that determines the risk that it's greater than 300.8 millimeters, which show at high risk, while 91.44 show medium risk.
In both paper and the presentation, you said that your model was good for a couple decades out to 2 centuries. What technique or what can you do to justify that statement? How do you know it's good for 2 centuries?
Well, I mean, once we created the actual normal model, we checked the data with short-term model, the short-term estimates, seeing how it adjusted with actual data looking at real life, as Albert mentioned, which is like the current conditions of each park. And once we found that the normal model did in fact work, statistical analysis we can use is the 68, 95, 99.7 rule, which states that 99.7% of all mean sea level increases that we see in that given year should fall within 3 standard deviations. So we find a benchmark of how far off our mean sea level increase would be. So that 18.84 estimate that we found in 1 century actually would show how far off that should be. Because realistically speaking, if 99.7% of all sea level increases fall from that one trend of 18.84 millimeters, then that 0.3% was not likely to occur. So we can sufficiently say that it should fall within these 2 benchmarks.
So also, like in time periods that are above 2 centuries, when testing our model, we decided that the range of possible sea level increases would be too wide to accurately determine whether it would be low, medium, or high risk at that time period.
So I have a question on your severity index for heat index. So why did you choose a 4-parameter logistic regression model, and then where do the 4 caution level reference points that you split up of those temperatures come from?
All right, so first to address the second part of the question, the levels of caution was based off of the heat index chart, which shows actually the relationship between temperature and the relative humidity, which gives it a heat index value. And in that chart, it also shows what heat index values are for which levels of caution, for example, danger or extreme danger, fatal, etc. And for the first part of the question, we chose to use a 4-parameter logistic regression because it makes logical sense. For example, a lower heat index doesn't the effective heat index grows exponentially at first, but then decays as the heat index value increases. So we chose a four-parameter logistic regression, and it also fit with the data that was provided, so it made sense statistically and logically.
For the hurricane, the severity index for the hurricanes, you weighted that much less for the west coast than for the east coast. However, I noticed that at least it seems intuitive to me that perhaps a park in Maine might have a much lower geographic chance, even if it is on the east coast, than a park in Texas or North Carolina. Did you take into account, why did you choose to make the basis on west coast, east coast?
Well, that was partly to simplify our model. So one thing I believe that we could improve given the time is to separate into more regions and develop a more accurate model based on that. So because we had limited time, so we were only able to separate into two distinct regions, East Coast and West Coast, which made it more simpler for us to model at the time.
In terms of that index, you added those numbers up and you used these weights. Where did these weights come from, and what does it mean to add those numbers together?
Well, the weight for visitor index, the 3-to-1 weight represents how visitor index is what determines how much profits each site brings in, which ultimately dictates how much funding the NPS has for future investments. Whereas vulnerability index just has an additional impact. Well, visitor index has the primary impact on profit.
Also, for the part 2 weights, the weights were chosen based on the effects of the factor on national parks in general. For example, hurricanes, as we mentioned, west coast versus east coast, the effect is significantly less to the west, so we weighted it less. For example, the effect of heat index is relatively constant, like it doesn't change based on east or west coast, so we chose to give it an equal weight in both the east and the west coast. And the other weights followed according to observations from past data and the effect of heat index, hurricanes, and air quality on national parks.
Following up on that question, I can get what happens when a hurricane hits a park. Can you tell me physically why heat index and air quality index matter to the rocks and the boulders and stuff?
All right, so for example, heat index consists of both temperature and relative humidity. So as temperature increases, that could have an effect on the ecosystem. For example, the rate at which plants can spread, or how different species can interact with each other. And similarly, for air quality index is more of a measurement of how clean the air around the environment is. And depending on the toxicity of that, that could also affect the plants.
And in general, when you consider the three main factors we did choose, a large part of our reason why we chose them were they do affect the biodiversity of each national parks, but also importantly, the ways we distribute funding are largely back into how the number of visitors actually attend that park. And for a park to be strongly susceptible to poor air quality, I mean, we've seen constant trends in today, especially people are less inclined to go places where they are in a position of being less healthy or more dangerous to them. So it makes sense to include all things, especially considering that human interaction, human visitation is also affected by these variables also.
Sorry, one further follow-up question. You said that, so you changed the weighting on the hurricanes between the east and west coast because of different geographic position, but the heat index should impact both east and west similarly, so you kept the correlations the same. Does the air quality index change at the national parks versus east and west coast? Because that coefficient was changed pretty significantly by adjusting the hurricane rates.
Yeah, so the air quality index changed as a result of the hurricane index change. So the effective air quality index and heat index in the West Coast were approximately equal, so we gave them similar weights. So the significant difference between the air quality index in the East and West Coast is partly due to the decrease in effect of hurricanes in the West Coast, but also because of its relative weight to the heat index.
Yeah, because in general, like, we did find a positive correlation, a negative correlation. I say hurricanes become more prevalent. We see like air quality index for some reason or matter. When we actually found our data to be like also because of this compensation, we weren't actually sure why. And in fact, our R-squared value was low. There was still a noticeable trend in the data. But furthermore, the reason why we do that is because when we actually compared data, it seemed that heat index was a very large factor. So we thought in comparison Halifax National Parks versus air quality, so we thought to decrease heat index, which is the main factor really that we sought out, at the expense of air quality, which wasn't as great a factor. We thought it was more suitable in our model to just accentuate the main factor that was affecting both parks, which is in fact heat index.
Great, thank you.
Thank you.